Hi, I'm David McIntyre, and I'm with Samsung Corporation. Today I'm going to talk to you about security as it pertains to computational storage drives. So in this talk, we'll talk about what are computational storage drives in the first place, and what sort of new security risks do we need to consider when dealing with computational storage drives. We'll look at some of the emerging security standards for computational storage, and then also address the risks around security features pertaining to the computational storage drives themselves, and then also other features in software, hardware, and system level considerations. And finally, I'd like to ask a call to action from each of you. So let's get started. So security has really rapidly changed over the last decade. There's been a significant increase in threats across data, and as such, we've seen things like, as of late, the meltdown from Intel in the late 2010s, and then we've seen the latest news about Microsoft had a big exposure data event. So basically, what's happened is these sort of events have catalyzed new storage security standards to be formed in response. As an example, Google OpenTitan was released in 2019, and also standards regulations that have also been another response to these events, from FIPS 140-3 in 2019 to the NIST SP 800 storage regulation, which was released last year. There are a number of initiatives that you can see also, from Open Compute Security Initiative to DMTF, SBDM as well, to address enterprise and manageability concerns. Now, if we look to the right on the data center security considerations, what we're dealing with here is really an edge to cloud to hybrid cloud, where you're dealing with on-premise considerations, and all of these points have potential threat risks. That is, an intruder, a bad actor, can get involved in IoT or sensors, or also attack data that's in flight between the edge and the cloud or on-prem, and then finally within the infrastructure itself, across the subsystems and devices, where you have firmware potential intrusions across both compute storage and intra-networking within the data centers themselves. So in summary, data in flight, that's an ongoing network security problem, but now we're dealing with data at rest, which can deal with theft of data or keys, especially solid-state drive media and key encryption in those solid-state drives. And then finally, actually, this is more of a response, hardware root of trust, where you can have a dedicated security engine to ensure secure boot, secure firmware, and key management across all peripherals. So let me give you an overview on what computational storage looks like and what the key value is. So the left-hand cartoon shows that the traditional interconnectivity between a CPU host and solid-state drives, and moving the data back and forth from the drives to the host for processing, along with DRAM support and perhaps an external FPGA bound accelerator as one example. The issue, as you can see with those hourglasses, is we're providing an opportunity for many bottlenecks for load imbalance, where data may be clustered at the compute, waiting to be compute upon, or just simply the transmission of that data from the solid-state drives up to the compute cluster. Well, this is where computational storage comes in as a way to provide better performance by basically providing and integrating the compute element within the storage drives themselves. This means that you can basically remove the necessity of moving data back and forth. There's no large data transfers anymore for targeted data, and you're able to get faster results for real-time critical-based applications where you can't contend with the latencies that you would normally get in a more traditional networking infrastructure. This also allows you to scale the acceleration so you're not dependent on the host resources. As you need more computational storage, you can simply add more to the array of drives that you have. And another benefit is that you're offloading the host processor, which allows it to be free to do other compute tasks up in the host cluster itself. Deployment examples here would include basically connecting the compute storage drives directly to the CPU host. Also, a smart cache layer can be implemented where you have storage tiering, where you, for your hot real-time applications, you can have computational storage drives connected to the host, where you have data which is more at rest in hard disk drives or solid-state drives as well, that don't need to have that real-time compute element included. And then the third category would be cloud-to-edge compute, where you're able to perform and provide computational results at the edge versus sending all that data, aggregating it, and then sending it back to the cloud for processing before you even know what the results are. So here's a potential implementation of a computational storage drive and some of the elements to be considered. So if you open up the hood of a drive, you might see a solid state controller and NAND flash, terabytes worth of flash. You may have DRAM as well, some level of DRAM for buffering. You could have an FPGA or an ASIC as well, performing the compute function, the acceleration function, as we call it, for that in situ compute in the drive itself. Or what that means is bringing the computation power directly into the drive. So now you're going to move the data back and forth, but it can be results of the raw data that you're computing upon, and have basically through having a peer-to-peer connectivity between the accelerator and the data itself in the solid-state drive, and then shipping that data up to the CPU host. So now on that right-hand illustration, you can see that you now have to contend with NVMe solid-state drive connectivity, as well as dealing with the accelerator as an additional functional block. So this means that, for one, as we talked about earlier, you're able to provide far more compute efficiency across this computational storage drive. But you do have to consider that now you're introducing additional components into this computational storage subsystem. So we need to go through each of those components and make sure that each one is properly protected so that your data is properly protected. And if we go up a next level, we're going to see here that you have a solid state drive down on the bottom hand here, and the connectivity to a host server, both in-band and out-of-band signaling, they need to be considered. And you can see that there are many attack points that perhaps that would not have been included with a traditional host to standard solid state drive development. So here you're now, but there's an opportunity to create, we call them root of trust blocks. So basically through encryption and keys and other mechanisms, we're able to not only self-encrypt the drives themselves, but also ensure that any functionality that is within that solid state drive or a computational storage drive can equally be protected. Let's spend some time on this diagram because it illustrates a lot of good points for us. So here we have the host clusters, and then an array of permutations of computational storage drives. So if we start on the left here, we can see here's a traditional storage drive where you have within it, you have a storage controller and the storage media and a management connectivity and IO connectivity for the data up and through the host. So this data is going to go up to the host cluster for processing, and the data at rest will stay within this traditional storage device. If we go one block over, now we're looking at a computational storage processor that provides a computational storage CS functional module, which had basically dedicates the capability of computing on that media, on that data, as well as a computational storage engine, which provides the specific device capability of providing functionality such as database offload, storage, functional compression or filtering, and so forth. So now we're adding additional complexity. This means just by the number of blocks that we're adding, those are more attack points for a bad actor to come into our system. Then if we look at the computational storage drive and the next one over, we can see now we're adding basically increased storage and a storage controller, whereas before we didn't have that capability, we just had the engine itself. And then if we move on further to the right, now we're providing access versus a computational storage processor, as well as direct access to the storage itself. So again, additional blocks that can be attacked. And then finally on the right, this is an illustration of an array where you can have an array of computational storage functions. And just by the nature of array, you have additional attack points to be considered. So that means that we need to take a look at adding and ensuring we have security functions, including authentication, which is basically authenticated connectivity between the host and those CSDs, authorization for addressing secure data access and permissions, encryption across the whole subsystem, and then auditing, basically able to achieve secure logs. If we look down on the left, we have risks versus standard storage. So the computational storage drive may delete, add, modify data on the drive itself. The CSD functionality may be programmed as well. As an example, an FPGA, which we'll talk about in the next slide. And also these devices can be virtualized. So as a subsystem, there's additional security features that we need to consider. Risks versus an external accelerator, say a PCI Express card. Here you have direct access to that storage. FPGA programming needs to be considered because as FPGAs can be used as that accelerator within a computational storage drive. And then also you have direct access via NVMe-OF through the network infrastructure. And this is a big one, the data would be most likely decrypted prior to processing. So that is another exposure point to consider. So there's a lot of different things to consider on just this one slide. So let's get even to the next level. I mentioned FPGAs. So FPGAs are typically used for accelerators, not exclusively. In fact, we're seeing more and more ASICs being deployed, but certainly FPGAs are quite pervasive for these types of accelerators today. They are SRAM-based devices which are programmed by secure bit streams. And the benefit of an FPGA is just that. It's a programmable device where you can change the programming to support different design types. So the way that's done is a key is programmed via a JTAG port. The bit stream, which is holding the design of that application, is encrypted with specific design tools that support that vendor's FPGA. And the FPGA identifies whether it's working on encrypted or no encrypted data for field testing. I would also say that you're able to update the bit stream in the field, which is a big benefit of FPGAs in production applications. Typically, you'll see an AES 256 security methodology used to program FPGAs. Now, here's a really interesting part is that you're actually able to design and isolate different regions across the FPGA, which allows you to provide basically fort or strongholds across the FPGA for enhanced security over different blocks, from the compute resources that may be there, the I/O, or the design SRAM resources themselves. You're able to partially reconfigure the device through just-in-time programming. So only when you're ready to do so, that gives you some additional security leverage, doesn't it? You're also able to isolate the system-on-chip SoC and bus, and also provide programmable user files, PUF files, for device dependency. That is, you can target specific devices in a good way, so they're only going to be implemented and able to perform for given identified customer use cases, and just not generically open to all. And in response to that, you can actually develop e-fusing, electronic fusing. So if a bad actor comes in, you can basically shut down the device itself. And that article that and the IEEE Explore goes into far more detail. It's a wonderful white paper that will give you further information on how FPGAs are protected for security. So what is SNIA doing around this grand topic of computational storage security? Well, there is a technical working group focusing specifically on computational storage, which addresses not only the host access and interfacing, but API standardization, and is developing many of these security issues that need to be considered. There's an expected release of an architecture spec from this group, fourth quarter of this year. And brand new is the SNIA Computational Storage Security Subgroup. And this is being refreshed to address basically and continue on from where this presentation provides a foundation into use cases, applications, and methodologies, moreover, to protect computational storage drives across all the applications that we can think about. NVMe, there's a computational storage task group as well, where they address device access, interfaces, and implementation. And they will have their latest release of the standard available first quarter of next year. So in composite, this allows the threats across storage infrastructure, bypass and offload, and within the computational storage engines themselves to provide a very strong and robust methodology for protecting these devices, and most importantly, our data. So I thought it'd be interesting to see how the cloud service providers are dealing with these new technologies like computational storage, which are coming to fruition. And I think it's important for us to understand that, of course, they have security policies in place today. And what they care about are some of these things that you see listed. So data in flight, processing requirements in data handling, buffering and caching from a memory standpoint, data at rest policies for storage, containerization, virtualization across all resources available. Multi-tenancy is a very big one to ensure that as a customer of that cloud service provider, your data is properly secured and there is no sharing of data across different tenants. Edge deployments for in-situ storage processing is something that the cloud service providers, the hyperscalers, in specifically are now considering to address that opportunity we talked about earlier for higher performance compute on the data itself at the edge. So let's go a little further into some of these expectations. So we will go through these 6 main categories, or pillars they call them, from a root of trust, cryptography, secure enclaves, self-encrypting drives, key management, and security life cycles. So root of trust, the Open Compute standard has said that the Cerberus root of trust is something to be seriously considered. So basically you are protecting each of the component level devices that you see highlighted in yellow squares within the subsystem itself. So that enables standardization for secure boot across all the devices on the platform. It prevents from physical and side channel attacks. It supports automated and secure key management. And here's an example of a Microsoft storage server with 40 Cerberus root of trust enabled chips. On the right, you can see Microsoft Cerberus components and another of supporting encryption methodology blocks that are within this particular block, from RSA to SHA to AES 256, and all the necessary security building blocks to provide that root of trust certification and capability. Here, if we look at cryptography, we can see that there are a number of standards that are recommended by different organizations that can provide different levels of security strength. So from AES to ECDSA and RSA, you can have a certain level of baseline robustness in your cryptography, or also be even enhanced to that. And then for secure enclaves, you're able to provide protection against physical and side channel attacks within a full enclave with monitoring, EMT, and timing resources. And this is an example of self-encrypting drives that basically can support these types of standards, and from single drives to volumes of drives to arrays of drives too. And key management is also a significant requirement and methodology for protecting your data and the security around that data, as well as the security life cycle. What happens from the design all the way through the retirement of that device. So these are just topping on those 6 pillars. And you can see that companies like Microsoft, Facebook, Google, they all are supporting these root of trust standards and the methodologies that you see here listed in this table. So call to action. We just went through quite a bit of information. I would really encourage you to participate in the SNIA computational storage technical working groups. Contribute the industry use cases that you know about that should be considered for security issues. Attend those SNIA computational storage, compute storage and networking events, and think security as you develop your own architectures and systems and designs. And feel free to join the SNIA computational storage security subcommittee. It's newly remodeled, it's addressing security threats and solutions for our industry, and it gives you the opportunity to participate directly in that. I hope you enjoyed the presentation. Thank you for your time.